This is section 17.7, Stokes Theorem. This is really exciting because Stokes Theorem, the divergence theorem, and Green's theorem are the crowning achievements of calculus. I have this picture here of like what we're going to be dealing with, but yeah, here's the goals. The goals of Stokes Theorem of the Stokes Theorem section are to use Stokes Theorem to compute a line integral and use Stokes Theorem to evaluate a surface integral. Stokes Theorem tells you that a certain line integral equals a certain surface integral, so you can take a difficult one of either type, often, and turn it into the other type, and maybe that makes it easier. The data types we're going to use here, we're basically using like every data type that we've come up with in the entire class. We're going to have vectors, of course. Then we're going to have functions from the plane to the real line. That's when you have a function whose input is points in the plane. That's what a surface looks like, and that's often how we'll build surfaces to do these surface integrals. Then we're going to have these paths in the plane and paths in space, which are functions that take input of like t, time, and their output is a curve, c. And then finally we've got vector fields. Vector fields are like the main thing that's powering all this stuff that we're integrating. So we've got all the data types here, we're putting it all together. It's kind of great. Let's figure out like what we're supposed to expect from this section. Essentially, Stokes' theorem is an extension of part of Green's theorem. So let's remember what Green's theorem in circulation form said. In circulation form, Green's theorem said, let's say that you've got a simple closed curve C. So it's a loop. It doesn't cross itself. And inside that curve C is a region R. And then you say, well, what if I've got a vector field F? And here I'll draw a vector field that's like, I don't know, a little tornado. And there's not much going on over here. If the vector field is conservative, then the walking around a closed loop will have net effect 0 on your walk. But in this case, this vector field is not conservative. As I walk around this loop, the vector field is helping, kind of indifferent, kind of indifferent, kind of indifferent. So in total, the vector field helped me. That's the circulation of the vector field around the curve C. That's this integral. We found in Green's theorem that you can calculate the circulation by going to the inside, going to this two-dimensional surface that the curve is bounding, and do a double integral of a certain object here on the region. This certain object was the curl of the vector field. Now this was the two-dimensional curl. We now know about the three-dimensional curl. So Stokes' theorem says, well, how can we integrate the three-dimensional curl to do the same trick where we calculate circulation, but do it in 3 dimensions? So here's the answer. The answer is a little bit complicated. It says, instead of having a flat, like planar region that has a curve around it, instead let it be like a goofy, wobbly surface in 3 dimensions. But it still has an edge, and the edge is this curve C. Then the question is, if you are walking around this curve C and you've got a vector field in 3 dimensions, so like a wind storm or a vortex of some kind, then how does the circulation of that vector field around this curve relate to some kind of integral that we can do on the surface? So it's not like we're shading in we can't shade in the curve anymore because the curve isn't on a piece of paper. The curve is like out here in space. So like, how do we shade it in? And the answer is, well, we do the integral on the surface, which is the reason that we had surface integrals as the previous section. So the theorem says that the line integral along C is equal to the surface integral of the curl of the vector field. Okay, so let's write it down first. Here's the circulation of the vector field on the curve C. Remember, we measure circulation this way because we're asking, does the vector field agree with the direction that the curve is going? When you dot 2 vectors, you're seeing like how much they agree with each other. Stokes' theorem says, yeah, sure, you can find this. You can find this by going to the surface and adding up all like the swirliness that's on that surface. The same way that we went inside the curve here and added up all the swirliness that was inside the curve. So how do we actually write that down? Well, I'll write curl F here. And then instead of seeing how much it agrees with C, instead I want to know how much it agrees with the normal vectors to the surface. And we'll do this integral over the surface. So you should think of this as essentially the same deal as Green's theorem in circulation form, that you can that if the vector field is helping you go around a loop, that means that the vector field must be swirling around inside the loop. And this measures that. A small notational thing is that sometimes this part, the n ds, gets combined together, and this is called ds with like a vector on the s. And I won't do that, but this will happen a lot, where people are trying to say you're just integrating the curl over the surface, but I don't know. We'll see. We'll see how useful that is as we go. Okay, there's some technicalities here, which is that it's a little bit tricky to figure out which way the normal vector should go. The normal vector to the surface, you could pick this normal vector to the surface, and you have to pick like a consistent set of normal vectors all throughout the surface. So like if you pick this way as out, you have to keep picking this way as out for the whole time. You could also just pick the normal vectors to go in, like just point into the surface. So like which one do you pick? And the answer is that you have to pick normal vectors whose orientation is consistent between the boundary C and the surface S. Okay, this is kind of tricky, but we've got, that's what this thing that I opened with, this picture that I opened with is about. So how do you get the orientation correct? So here's my attempt at can I spin it some other way? Yeah, okay. So here's our curve. Having trouble rotating it in a reasonable way. Here's our curve, and it's oriented in some certain direction. We'll say it's going around this way. That's what this red arrow is supposed to be showing, but it's hard to see. So it's going, like, the part of the surface that's close to us is going to the right, and the part of the surface that's away from us is going to the left. So the curve is going this way. How do you pick normal vectors that agree with that orientation? The answer is you try a normal vector. This one is pointing out of the screen, out at us. And you go and you set up the right-hand rule so that your thumb is pointing the way that the normal vector is pointing. Let's see if I can get it to work on the screen. So it's backwards for me. So you set up your thumb so that it's pointing the way that your normal vector went. If your hand is curling the way that the curve is going, then you've done it correctly. So the curve of your fingers is on this picture represented by these like swirly circles. And you notice that the swirly circle, when it gets down close to the curve, is going the same way as the curve. That means you've picked the correct normal vector. If we picked normal vectors going in instead, that would agree with the orientation where the curve was going the other way. So this is kind of like an obnoxious detail, but it ends up mattering because if you get it wrong, you get the opposite of the right answer. I think the examples we're going to do, almost all the answers are 0 anyway. But yeah, so that's what it means to pick an orientation that's consistent with the curve. The idea of Stokes' theorem is that like it doesn't matter how wild and crazy the curve is, you can always still do this as long as the curve is smooth and the surface doesn't have anything super crazy going on. You can pick normal vectors that are consistent everywhere so that the little swirly pictures are always, like the little swirls are always agreeing with the orientation of the curve. Okay, I've spent a lot of time on that specific detail. That's not like the hugest detail, the hugest most important detail. The huge most important detail is that you see how Stokes' theorem and Green's theorem are connected. That both of them say, to find the circulation of a vector field around a closed curve, you look at a 2D thing that's inside the closed curve. In 3 dimensions, it might be a wavy surface that you're using to like fill in the curve. In 2 dimensions, it's just you shade in the curve. in both cases, the circulation integral is equal to a double integral of the curl times like dA, or in 3 dimensions, ds. So you find the circulation by adding up the swirliness on the inside. I don't know if you remember, but at the very beginning of the class, we had a there was like a comic on the front page of the of the D2L page. And it was this one. And I love this comic. It says, "The more complicated the math, the dumber you sound explaining it." Stokes theorem? Yeah, that's how if you draw a loop around something, you can tell how much swirly is inside it. So this is, the circulation is equal to the integral of the curl. Yeah, we can do a little better than this, but it does sound kind of ridiculous, and I like it. Okay, let's, I think we get to just do it, because we know how to do surface integrals from the last section, and we know how to do line integrals from forever ago. So let's do one. Of course, the worst thing that's going to happen to us is that we'll have to parameterize a surface in order to do a surface integral. So the first example says, verify that Stokes theorem is true, which means just compute both sides of Stokes theorem and show that they're equal. Usually when you use Stokes theorem, it will be because either the line integral is hard and you'd rather do the surface integral, or the surface integral is hard and you'd rather do the line integral. But in this case, we're just going to do both. So Stokes theorem says that the circulation of the vector field on the curve C is the surface integral of the curl of the vector field on the surface. So let's just do both. Let's get the hard one out of the way first. So we'll find the surface integral first. How do we do that? Well, we'll have to find the curl of the vector field. The curl of the vector field is del cross the vector field. This was the way that we defined it, where del is this partial x, partial y, partial z. So we've got ijk, partial x, partial y, partial z, and then the vector field. And we're finding the determinant of this matrix. The way I've been finding determinants in this class is to just copy down the first two columns. And then go forward. I get 0. Get 0. Forward, I got partial z of minus z. That's minus 1 in the j component. Partial x of x is plus 1 in the k component. And then go backwards. Partial y of minus z is 0. Partial z of x is 0. And partial x of 0 is 0. Okay, so the curl of f is 0, minus 1, 1. Okay, now what will we have to do? Well, the hard part, of course, is finding what n is, our normal vector that's consistent with whatever direction we're going around this curve. So now we have to actually deal with the surface and the curve, which is usually the hard part. So this surface is the unit hemisphere. It's oriented outward. You can see this normal vector pointing out. So when we get our normal vector n, we just have to make sure that we pick the right one. It doesn't seem to tell us which way the curve is going, so I guess we'll have to use this orientation to figure that out. To figure that out, you imagine a little right-hand rule with a thumb pointing out, and that means that if you drew those little loops, that it tells you which way the curve is going. So the curve must be going this way. So the curve C is this loop in the YZ plane, and the surface is half of the unit sphere, and it's just for the negative x's. Okay, so let's try to do this. Let's try to do this integral. It's a sphere, so you can probably guess what my favorite parameterization is going to be. My favorite parameterization will just be the spherical coordinates. And with radius 1, I'm just going to copy down what it comes out to. This will be, this is like phi, and this is like theta. It's the unit sphere, so rho is 1. So here's my parameterization of the surface. This will allow me to figure out what ds is. What is ds? Oh, right. This thing. This is the nice cancellation thing that we had before. So this comes out to tu cross tv dA. Let's put that in a box somewhere so that you can remember it. So n ds is also known as ds with a vector. And this comes out to tu cross tv. I'll just write dA. It's du dv or dv du. So let's put this in a box so you can use it when you want to. So we have to find tu and tv. Those are the tangent vectors in the u direction and the v direction, and cross them. So I have to do tu. It's the u partial derivatives of this thing. And tv, the v partial derivatives. And then we cross them. Is there any way out of this? I guess tv has like a common factor of sine u. So tu cross tv is, I have this sine u that I've taken out, and then I do this cross product. Tu goes here. I didn't leave enough space. I never leave enough space for the cross product. Maybe the problem is that I write the ijk first. Let's not write the ijk first anymore. I need the determinant of this matrix. I'll do that by copying down the first two columns. I feel like I've done this exact thing before. Oh well. In the I component, I get 0. In the j component, I get minus sine u sine v. In the k component, I get cosine u cosine squared v. Then going backwards, I get plus cosine u sine squared v. This way is plus sine u cosine v. And this way is nothing. So in total, tu cross tv is, it's got a sine u, and then it's got sine u cosine v minus sine u sine v. And when these add together, this adds up to 1, and I get cosine u in the k slot. Okay, seems good. So I have curl f is this vector. I have nds is this stuff, so I can put it all together. Curl f dot nds is the integral over the region R instead of the surface S. When we get actual parameterization in here, we get to use our parameterization's bounds of u and v. Curl f was 0, minus 1, 1, which was right here. And then nds is all this stuff. sine u is a scalar, so I'll just put it at the end, I guess. I'm worried that this is going to come out to 0 and that's going to make you sad. But whatever. It just kind of looks like those arrows aren't actually helping or hurting. Oh well, so let's do the dot product. The dot product of these vectors is 0 times the first component, whatever, minus 1 times the second component. So I get sine u sine v. And then 1 times the third component, which is plus cosine u. This all is multiplied by sine u. And then I've got du dv here. Now the question is, what's going on with u and v? What are the actual bounds here? Like, I have the part of the sphere that goes, that's like for the negative x's. So what is that? Well, I can tell first of all that the phis go all the way from 0 to pi, because the North Pole up here is included, and it includes everything all the way down to the South Pole. So phi, that's u, is going to go all the way from 0 to pi. V, that's the theta, that's the longitude. We don't have every longitude represented here. Like, here's theta equals 0. It's not on this part of the sphere. It starts at theta equals pi over 2. And then it goes all the way till theta equals 3 pi over 2. So the bounds are from pi over, the v bounds are from pi over 2 to 3 pi over 2. Okay, let's do this. Is there any reasonable way to do this integral? I'm going to multiply this sine u in because I don't see any way to do anything with it out there. What did I do in my notes? In my notes I did it in the other order. Well, that doesn't really help anything. Like, we would need to do some power reducing stuff, and well, the other order is a lot better, because the integral of sine v from pi over 2 to 3 pi over 2 is 0, so we would get rid of this part entirely. Oh well. Let's just ask the computer to do it. It's too ugly. So we've got, that's not the one I want. We've got the integral from pi over 2 to 3 pi over 2 of the integral from 0 to pi of sine squared u sine v plus sine u cosine u. And this is du dv. I think it's 0. It's 0. So this integral comes out to 0, this surface integral. I haven't really decided what exactly is the time that it would make sense to go and switch to like when do you do the integral yourself, and when do you have the computer do the integral for you? I don't have like a universally correct answer to that. I guess ask your instructor whenever you're taking this class. So this was the surface integral. We just like straight up did the surface integral over the sphere. Stokes theorem's kind of like philosophy is that if you ever have a surface integral that you don't want to do, you never have to do it again, because you can just do, okay, if you have a surface integral you don't want to do, and there's like a boundary for you to integrate over, then you don't have to do the surface integral. You can just do the line integral instead. So let's see how much easier the line integral is. Can I like just cut off part of this so that I can, yeah. So now we'll do the line integral. And it's not like the line integral is always easier than the surface integral. Sometimes the surface integral is easier, but yeah. Okay, so how do you do line integrals? To remember how a line integral works, you need to parameterize the curve and then take the derivative of the vector valued function that defines your curve and dot product with the vector field. So here's my curve. It's a circle. I need to make sure that it goes around this way so that it agrees with the normal vector that I had. X is always 0. And then let's just try cosine t sine t and see if it goes around the right way. If not, I can just swap them and I get a different direction. So cosine t sine t means at t equals 0, I would get 0, 1, 0. And at t equals pi over 2, I would get 0, 0, 1. So I start at 0, 1, 0 and end up at 0, 0, 1. No, that's backwards. That's going the wrong way. So I'll switch them, and then it will go the other way around. There's probably a better way to do that, but I don't know. I don't feel like memorizing it. So this goes like clockwise, and so if you switch it, you'll just go the other way. T will go from 0 to 2 pi. So this is our r. dr is just the derivative of this thing, dt. And then what was f? Well, f was a vector field that was minus z x 0. Okay, this is where students get stuck all the time in this class. Too many variables. There's variables everywhere. What do I do with z? What do I do with x? And the answer is your parameterization tells you what to do with it. Z is cosine t. X is 0, according to your parameterization. Now remember, the idea here was Stokes' theorem lets us get out of doing the surface integral if we don't want to do it. Instead, we can do this line integral. Why is this line integral better? Well, look at the dot product of these two vectors. Cosine t times 0? Okay. 0 times cosine t, and 0 times sine t. 0. We did it. Stokes' theorem promises that those integrals are equal. We just happened to calculate both of them, like brute force do both of them, and they both came out to the same thing. Yeah, normally you won't do both sides of Stokes' theorem. You'll actually use it to conclude something. So let's see, I think, one example in both directions, and that'll be enough for a whole section. So first, this one will say, here, I want to know the surface integral. I want to know how much, like, swirling action there is across this whole surface. And here's the surface. And you go like, what? The surface is insane. Like, it's some kind of weird tube thing? How am I supposed to... What? And the answer is, Stokes' theorem lets you get out of surface integrals by just dealing with the line integral on the boundary of the surface. So here's the opening of the surface. That's all you need to actually deal with. So you say what you like, invoke Stokes' theorem. You say, here's Stokes' theorem. I don't have to do the integral of curl f dot ds. I'll just do the line integral around the closed curve instead, the circulation integral. Okay, it tells you that the surface is oriented outward. So you've got normal vectors pointing this way. If your thumb was pointing that way, then the like swirls would be going... Oop, I have the eraser. The swirls would be going this way for your right hand. Yeah. So that tells you which way the curve is supposed to go. It goes this way, to like align with the little swirls that are on the surface. So to actually do this line integral, we will have to parameterize this little tiny circle. It's the circle it's like sitting here on the z-axis in the xz plane, and it looks like it goes up to 2. 1, 2. Do we get any better info than that? No. Okay, so this is my curve C, and I need to go around. This is the positive x-axis. The bottom is supposed to be going toward the positive x-axis, so it'll go this way. Does that look right? It's spinning this way. The positive x-axis is over here. So the top of the curve should be going away, the arrows should be going away from positive x, and the bottom of the curve should be going toward positive x. Yeah, so it's this way. Okay, how do you parameterize a curve like this? Probably the easiest way is to say, oh, this looks like it's just a regular old like unit circle because it has a radius of 1, except somebody moved it up in the z-axis by 1. So I start with cosine t, sine t. Y is 0. I'm in the xz plane. And then I say, wait, but it's up by 1, so z is 1 higher. And t goes all the way from 0 to 2 pi. So I'll do this integral using this parameterization. So what's dr? Dr is the derivative of this vector valued function, dt. And then I had f earlier was given by some crazy formula for whatever this vector field is. The arrows are drawn here. Z, 2xy, x plus y. So now I can find this line integral. I'm not really thinking about the whole line integral all at the same time. I'm like, what's f? F is this. What does dr mean? Dr is the derivative of r dt. So here it is. Wait, it's a t integral. That means I need t bounds. So t bounds go from 0 to 2 pi. Now I need to do this dot product, but it looks like a total disaster because there's t's and x's and y's and z's and everything. Right, the parameterization rescues me from that. The parameterization tells me that this is x and this is y, and so on. So what's z? Z is 1 plus sine t. 2xy, well, y is 0, so that's 0. X plus y is cosine t plus 0. Is this one 0 too? I don't know why the answer being 0 is unsatisfying, but this just feels like it's about to happen again. So we do this dot product. I get minus sine t minus sine squared t plus 0 plus cosine squared t. It's looking like 0. These integrals, whatever they are, they're the same, so they cancel. And this integral is 0. Is there like any easy way to see that? Oh, there's a trig identity that lets us say cosine squared t minus sine squared t is cosine of 2t. And then we can do the integral. Integral of minus sine t is cosine t. Integral of cosine 2t is half sine 2t. And we'll go from 0 to 2 pi. When I plug in 2 pi here, I get 1. And when I plug in 2 pi here, I get 0. When I plug in 0 here, I get 1. And 0 here is 0. So I just get a total of 0. It's a little disappointing, but the power here was that we didn't have to do the surface integral. Like, if you dislike surface integrals, Stokes' theorem is here for you to make sure that you can get out of some surface integrals. Yeah. So we had this crazy surface. It would have been basically impossible to deal with, but we just dealt with the boundary of the surface instead, this curve C. And it came out to 0, but whatever. Okay, let's do one more where we go in the opposite direction, where the question wants us to find a line integral, and we will say, you know, actually in this case, the surface integral would be easier. So we want to know the circulation around a curve, and here is our vector field. C is made of 3 line segments. Something in the first octant, so I'll draw the first octant. It's the 3 line segments that go from 0, 0, 8 to 2, 0, 0 to 0, 4, 0 back to 0, 0, 8. So there's a vector field swirling around. This like triangle is hanging out in a storm, and we want to know if the storm is in total spinning with this triangle or against it. The answer is, I don't want to do 3 line integrals with 3 line segments and add them up. That sounds super obnoxious. Instead, I will always vote for a single surface integral when the surface is a plane, like just a triangle. So plan is, I don't want to do this line integral because I would have to do it in 3 parts. Instead, I'll do a surface integral. And you should be highly skeptical. You should be like, you want the surface integral? But here you do, because it's just, it's part of a plane. It's easy to get a normal vector for a plane. This we did way back in the beginning. If your plane is this plane, 4x plus 2y plus z equals 8, the normal vector is 4, 2, 1. Well, this is a normal vector. You'd have to divide by its magnitude. 16 plus 4 is 20, plus 1 is 21. The only thing we have to check is whether this is pointing the right way. If this normal vector is pointing out from the origin, it's like coming out of the page, like this, I guess, out of the page, because it's like all its components are positive. Does that agree with the circulation direction of the curve? Well, the circulation direction of the curve implies that I'm supposed to have little swirls like this, because that would like agree with the curve on the edges. And if you have your right hand curving that way, then yeah, it actually does, your thumb comes out. If it had come out the other way, then you would just put a minus sign on the outside of your normal vector. But here's my normal vector, 1 over root 21, 4, 2, 1. Okay, so we'll have to find the curl of f. That's a little bit annoying, but this other stuff is just not hard. So let's do it. And we're getting out of doing 3 line integrals here by doing 1 surface integral. So curl f is del cross f. So it's the determinant of this matrix, where del goes in the 2nd row and f goes in the 3rd row. I'm doing this by copying down the first 2 columns. I think my handwriting has gotten a lot worse. Hope it's readable. So we go forward. Partial y of this is minus 2y. Partial z of z is 1. Partial x of minus z is nothing. Partial y of z, we're going backwards now. Partial y of z is nothing. Oops, that's in the k slot. Partial z of minus z, that's minus 1. and partial x of this mess is 2x. So in total, here's curl f. Minus 2y minus 1, 1 minus 2x, 0. Huh, that's interesting. That if your curl is all in the xy plane all the time, that means that the rotation axes are all in the xy plane. So everything is always spinning this way and never this way. If things were spinning this way, then the normal the curl would point up sometimes, but the curl never points up. Okay, so that's curl f. We got n. What is ds? ds. I feel like there must have been some better way to do this, but this is where we are. So our circulation is equal to, this is Stokes theorem, is equal to curl f, which is this thing, dot n, which is this thing, ds. Okay, what's ds? ds is, back when we had surface integrals, there were like two kinds of ds. One was where you like had a parameterization for your surface, and one was where your surface was explicitly defined. So if we go back to I'm just going back to 17.6 to see how this worked. 17.6 said that the integral of f dot n ds, which is what we're looking for, is the integral of f dot, this, f dot this instead. So we're doing curl f dot n, which is fine, it's just some other vector field. But I found n directly, which I guess was not smart. I could have just done this. Crap. Sorry. We didn't waste much time, though. It was just this part that was wasted. The trick in 17.6 was that if your surface is given explicitly by a function, then you can just use some partial derivatives, and your nds all together is given by this thing. So what is minus zx? Well, z was 8 minus 4x minus 2y. So minus zx is the x partial derivative of this function, but then flipped. So I get 4. Minus zy is the y partial derivative of this, but flipped, which is 2. And then I get a 1 here. So what goes here is actually 4 to 1 dx dy, or dy dx is probably easier. So I guess the square root of 21 that I found was the part that was wasted, the time that was wasted. Okay, so I need to dot these together. I also am going to need to figure out what the bounds of my integral are. So dot these together, I get minus 8y minus 4 plus 2 minus 4x. And this is all dy dx. I kind of want to do this all, like redo all of this, but there's only finite time in the world. So this 4 to 1 dy dx comes from this insight we had when we were doing surface integrals. Okay, let's finish this. How do I do an integral? Well, I need to find what the bounds are, and the bounds are now xy bounds. So I can look at what's going on and go down into the xy plane. And in the xy plane, we have a little triangle, and the triangle goes out to x equals 2 and out to y equals 4. We're looking at this region. What is this region? Well, this is the region where, like, this is the region when we look down on our triangle, what it looks like in the xy plane. And this line comes from the plane where z equals 0. So what is this line? This is y equals 4 minus 2x, I guess. So my bounds are x goes from 0 to 2, and y goes from 0 to 4 minus 2x. This should be enough for us to actually finish the integral. So the x integral waits for us. The y integral is minus 4y squared. This is minus 2, so minus 2y minus 4xy from y equals 0 to y equals 4 minus 2x. These are all 4 minus 2x. Can I do like a u substitution? I wonder if I could just do a u substitution and avoid finishing this integral. I just really don't want to do it. I'm out of space. I think there's something to be said for just like having another piece of paper, and that having a whole bunch of space on your paper actually like helps your morale a lot. As far as a problem goes. Let's be crazy here and pretend like we have lots of space. And then I'll get this copied over into a new page. So I'm doing the integral from 0 to 2 of minus 4 minus 2x squared minus 2, 4 minus 2x. Like, we can't be defeated by this integral at the end of all of calculus. Minus 4x, 4 minus 2x. Like, we've learned literally almost all of the calculus sequence. This is a single variable integral. We can do this one. Okay, 4 minus 2x, the quantity squared, is 16 minus 2 times this. That's 32. Plus 2x squared. Distribute this minus 2. And distribute this minus 4x. Then I need to distribute this minus 4, and I can finally collect some like terms. This one does not look like it's going to be 0. Okay, collect all the like terms. Minus 64 minus 8 is minus 72. Plus 128x plus 4x is 132. Minus 16 is 116x. And then minus 16x squared plus 8x squared is minus 8x squared. Looks like I could have gotten an 8 out of here like forever ago. Oh, maybe not. Okay, let's do the integral. 58. Oh yeah, very much not 0. So I have minus 144 plus 4 times 58 minus 64 thirds. Looks like it's coming out positive. My calculator told me that it was 66.6 repeating. What is that? 200 over 3? Cool. Okay, that's the last problem of all of Stokes' theorem, so I'm going to check this to see if it came out right. How can I check it? I guess I can ask a computer to do this double integral for me. That would be a good start. Let's see what browser window we get. Okay, that's good. So this double integral was the integral from 0 to 2 And then the integral from 0 to 4 minus 2x of minus 8y minus 4 plus 2 minus 4x dy dx. And I got 200 over 3. Oh no. That's not good. Okay, let's fix it. It's supposed to get minus 184 over 3. What did I get when I did it before? Minus 88 over 3? Well, this is going well. Whatever. Let's see what we did. So I had minus 8y. Its integral... Sorry, let's go back to this. Minus 8y. Its integral is minus 4y squared. Seems good. Minus 2. Its integral is minus 2y. This integral looks like this. Drop 4 minus 2x in where all the y's are. Okay. So now I'll ask the computer to do this integral to see if I did that algebra correctly. So if you have a long calculation, you can just like have the computer do intermediate steps and see if the answer is changing. So the integral I have here on the page, when I ask Wolfram Alpha to do that crazy integral, it still gets minus 184 over 3. That's the same value that I got from this integral, so that implies that from here to here I had it correct. So probably I copied it down wrong when I switched to a new page. Let's see. Minus 4, 4 minus 2x squared. Minus 2, 4 minus 2x. And minus 4x, 4 minus 2x. It looks like I copied it down right. Okay, maybe I squared something wrong. 16, 2 times 8 is not 32. Okay, let's see if that's enough to fix it. 4x squared, 8 minus 4, 16 minus 8. Okay, this 16 means that this is half as much, which means that instead of this term, I have 64 plus 4 is 68, minus 16 is 52. Integrating that, instead of 58, I'll get 26. And then 26 times 4 is 80, 24. So now I have minus 40 minus 64 thirds. And that's minus 120 thirds minus 64 thirds. So it's minus 184 thirds. Cool. Hopefully you don't think me messing up a problem and then showing you how to fix it is a waste of time. This is the kind of thing that like you can do when you have a long problem that you have wrong. Like ask the computer to do the first step. Ask the computer to do your middle step. If they're different, it means you made a mistake in between, or you typed it in the computer wrong. And then you can keep doing that, and you can eventually, it's called a binary search, find your error and fix it. So this one came out negative after all. Did we have a picture of it? I don't remember. We didn't have a picture of it. So I don't know. But this means that if you went around this path in this windstorm, the windstorm would be in your face, like working against you. Okay, that was Stokes' theorem. It says that a line integral that calculates circulation can be done by doing a surface integral that adds up the curl, the contributions of the curl on the inside. It's what Green's theorem said, but up in 3 dimensions. It's super powerful. Actually doing it is super technical. You should like feel super accomplished when you do these problems. And I've said super in every sentence for like 10 sentences in a row. So I'm sorry. Do some problems. It's awesome. This is a grand achievement of your math career. See you for the last section.